So good afternoon, everybody. So we are starting the afternoon session, and with the afternoon session, I sent a file. So I don't know if everybody has gotten the file. So the file I was working on this morning, or we were working on this morning, is the same one we'll go through. It now covers things related to how to create files yourself, and also how to create classes yourself. Okay, so there are two examples there to create classes. A simple, very simple example of using matplotlib is there also. So this is what we're going to use. So to get started, I think we should be on the same page. Meaning, yeah. So we should be on the same page, meaning everybody should be able to launch Jupyter Notebook. Okay? So this is what we'll start with to make sure everybody is able to launch Jupyter Notebook. Sorry. Yes. Huh? Yes. I think okay, what I'm going to do is I'll put the files on the flash, and then I'll pass the flash around. But the first thing you should do is make sure you can open Jupyter Notebook. So if you have a laptop, make sure you can open Jupyter Notebook. If you are seated at this computer, the Jupyter Notebook. Yeah, I sent it fast to your email.
So we have to find it.
Oh, yeah. I'll send to you. So it's either okay, you collect from either. Yeah. So okay, I will know. I'm sorry. Okay, if you've not received the email, in the email there's a Google link there, and then the file is exactly there. Oh, yeah. So the file is exactly there. There's a drive. So I hope you can all reach the drive. Okay, so I'll try to forward it to all the people that don't have. So it is Ida and voila and sustain and with mail. Okay. Maybe Sunday also. Oh, I'll explain to you. Henry, Elizabeth. Okay. Dennis. Consulate. Abdallah. Okay, so you should all have received an email with a link, and in the link you should be able to download the file. Okay, the main file you need is intro to Python notebook, and then in the folder there's a folder file. There's this folder there with the same. And then two other files. So we use this. So because I have people like you, I'll try to finish the lecture. So some of them are processed here. And they have a class.
I'm a problem at all. It's just want to be sure that we are not missing anything.
Oh no, they have a class. Oh, Yeah, but okay. Okay, so this is the first thing to make sure everybody is able to have Python. So you should be able to launch Jupyter Notebook on your laptop or on your desktop. Oh, you can use it. Is everybody able to do this? If you need to install the password is like this one on the board, EAIFR was 4 letters. So when you start, you should navigate to where those files are. Okay. So you should go to where those files are. You should navigate to where those files are. So it's important. The reason is because it's easier, okay, to work in the same folder where those files are. Yes, you can always use some other.
We have not been able to do that, sir.
Oh, okay. Have you been able to download the file?
Yes, sir.
Okay. Now the next thing is you have to navigate to where the files are. So let me behave as if I'm.
Wow.
Yeah, too. Everyone give us that joke.
Okay, so someone said I have not received the file. Please check your email if you have received an email. Yeah, please check your email. Yeah.
We have like many files.
Yeah, check your email if you have received. So there's this intro to Python. Actually, when you start it, there will be no problem.
We have received it.
Okay, thank you very much for.
You are welcome. You are welcome.
Yes. In the chat, Ahmed put the file there, so thank you very much, Ahmed. What? Oh, you can't open the file. You should be able to. Oh, yeah. Okay, let me give it to you. Okay. Is that all right? Oh yeah, okay. So it's Day1, right? Yes. So we can Day1. Yes. Oh, there's something on it. There's an image that is just forgive about that. The image is just the image of the part of the website of that. was in my presentation that I forgot.
No, I want to see those files.
So, no, you should download it now. Then, once it's downloaded, what you need to do now, if you're on the Linux machine, so you need, well, even if you're not on the Linux machine, you need to open Jupyter. You can't just click on the file or anything. You need to open Jupyter. So, if you're on the Linux machine, you press Ctrl Alt T, the terminal will open, and then, okay. If you are using the desktops that are here, okay, you do Ctrl Alt T, then the terminal will open, and then you can just type Jupyter-notebook, and then you should be able to do it. Jupyter is JUPYTER, and then dash notebook. So if you are using the desktop, so if you have your own laptop, make sure you have an Akin installed. And then you can use Jupyter. Yes. So has everybody been able to open it? So I'm going to do something similar just now, and I'm going to show you what to do. Don't mind that I will show you in Windows, although I talked about Linux. Okay. Don't mind, but I'll show you in Windows, although I talk about Linux. So how do I open my Jupyter in Windows? Okay, I'll show you how I do that. So for me, is already here, Jupyter Notebook and Anaconda. But if it's not, if this is the first time you've installed it, you have to go to the files. Okay, sorry, I'm using an old Windows, Windows 7. So I go and I look for Anaconda 3. And then I launch Anaconda Navigator. So I launch Anaconda Navigator. Okay. So if you install Anaconda, there should be Anaconda Navigator. So you can look for it and launch Anaconda Navigator. So it's taking some time to come up now. Oh, sorry, I should share my screen.
So which one are we using?
Yeah, there's an introduction to Python notebook. Unfortunately, if you double click it, it's not going to work. So you first have to open your Jupyter notebook and then navigate to where the introduction to Python notebook is. So I'm going to do exactly that just now. So I'm opening my navigator. This is assuming this is the first time that you've installed, I mean that you've just installed Anaconda, and then this is the first time you want to use Jupyter notebook. So mine is opening up, and then once it opens up, I'm going to choose the Jupyter notebook, and I'm going to launch it. It's taking quite some time for me to, but it's loading it still. Okay. So I'll just be patient and it's going to load it. You can see some green thing that is coming up anyway. It asks me some questions. I say no, remind me later. Okay, so this is the screen I get after I do have Anaconda Navigator. So I'm behaving like a beginner here. So this Jupyter notebook is what I want, not Jupyter Lab, Jupyter notebook. Okay. So I'm going to go here to launch it. So I launch it. So it's going to open the Jupyter notebook in the browser. Okay, so it's opening it for me. Yes, so it has opened it in the browser. When it opens it in the browser, I don't see where my Day1 is. So you have to go and look for where Day1 is. This Day1 that I have I know where it is saved. So you have to know where it is. Okay? So I'm going to navigate to where it is. For me, I think it's in documents. Okay? So I navigate to my documents. Okay, because I already know this is where I downloaded this. For you, it could be in downloads if you downloaded it in downloads. For me, it's in documents. And then I have to go to IFA. So I click on this. So I'm navigating to where the folder is, and then I'll launch it from there. Does everybody understand what I'm doing? I'm going to exactly the place where I put the folder. So
You have to unzip the folder.
no, I don't think it's zip. No? This is zip? No, it's not zip. So in IFA, now I have to look for. So you just have to look for where it is. I kind of remember where it is for me, so I'll look for where it is. So this is what I mean by navigate to where it is. So you have to have an idea of where it is, and then I navigate to the place. Okay. So for me, it's inside here. So I go to MLESMP, and then inside it will be what I need. I'll look for Day1.
Is the one that download is in?
I can't even download it.
There's a folder, and the folder is called Day1. So yeah, if you are here, you can download it. You should have it on the flash.
I opened that flash. I was not seeing anything.
Okay, so I go to Day1 because it's there, and then in Day1, as you can see, yeah.
Something inside.
In Day1, as you can see, I have 4 files.
Not the files. They are in your machine. I swear. Oh, that's from there, and I can't download it.
So there are 4 files: intro to Python.ipy notebook. There's jump.xyz. There's pandas demo.csv, and there's water.xyz. So now I'm going to click on intro to Python. So I click on intro to Python, and then the file that I had from the morning will be there. Some will say, what if I want to create my own new file? Okay. Yes. So it's loading once I created it. So you navigate to where it is. It's loading now. So I have this introduction to Python. Okay. And I'm going to go through it. What if you want to create your own Python notebook? Okay, not one that is given to you already. Okay, this is straightforward to do also. You just go to new and Python 3. So if I click new Python 3, it will create a new Python 3 notebook. Okay, so you can do either of this. Okay, the one I gave to you, the first one is easier because I typed all the commands there already. I just have to follow. So let's go to this intro to Python. So like what we had before, this is the topics we are going to deal with. We've gone through the topics, and I think we were on NumPy or Pandas. Yeah, we were on Pandas. So one thing you can do is I have this because I have the file. Okay. One thing is you can execute each file each cell one by one, or if you are too lazy and you could go to you could go to cell run cells, or you can go to run all, and it will run all. Okay, and it can run everything. But my advice is that you go one by one and run each one in turn. Okay, so to run each one in turn, try to understand what everything is doing. So what I'm going to do now is I'm going to try to finish what we did in the morning, what we were doing in the morning, and then so I'll try to do what we're finish what we were doing in the morning, and let's see. Okay, we did pandas. Yeah. So I'm going to start from this part of pandas. So pandas is a library that you can use to create different data frames. Okay. So is everybody on the same page?
Excuse me.
Yes.
I'm still having a problem downloading the file.
Oh, still having a problem downloading the file. Okay.
Network is not my machine.
But were you able to download it?
Yes.
But some
If
people
I
don't-
should-
we
no,
don't-
no, no,
we don't
I
get to
download
the-
and it's, yeah.
Okay. Well, were you able to download it?
No, I didn't try it, but I can try this.
Did you download it?
I should
I mean, I can't use this.
Okay, you can. So it's good download it.
But then she is, need different network. She's on my.
Oh yeah, she was.
She can be able to.
Yeah, it depends.
She can attend our Zoom meeting, she could be able to.
Okay. Okay, so I'll wait a few minutes to make sure everybody is able to download it. Yes. You download it? So let's do this quickly. We go down to pandas, and then we'll try to finish up our pandas. I'll tell you a little bit about matplotlib. I'll tell you about pandas, about matplotlib, and then yeah, I'll tell you about object-oriented programming. Don't be scared about it. Just think of it as a way to create your own data types. There's int, there's string, there's float. You can create your own. You can call it your own name, and it has different things, and it will have functions also, just like string has function. I'll show you there's a way, no matter the string you type, you want to convert everything to uppercase, there's a function you can call, a method that belongs to the string class that you can call. So you see how to create your own class just now also. You create your own class, and you can do different things with your class. So this is what we're going to do now. I'm going to start with pandas, then do something quickly with matplotlib, then object-oriented programming. I think this is where we'll stop. Later on in the week, maybe tomorrow or the day after, so really get into machine learning. Okay, so I think everybody should be now on the same page. Okay, so we did this in the morning. Import pandas as PD.
You a statistician. You say they are showing statistics. Ah, data science. Data science.
Yeah. So there's this array one which we created before. So I have to look for it and execute it. My list. Do I need my list? I think. Oh yeah, because I need my list. No, yeah, you can start all and then until, because I feel we're not going to have enough time. So that's why now I still have to look for it, which, yeah. So I go to NumPy module above it. So I'm going to execute this.
Sorry, the one we have to upload is.
Yes.
I should check that.
Okay, so I went up to NumPy module. You can look for NumPy module in the title, and then I executed it. The reason is because I need array1 and array2. I hope these are the only two things I will need. Okay. So once you do that, then you already have array1 and array2 defined, and you can use it in your Pandas module. Okay. So with the Pandas module now, I'm going to execute this now. So it's taking some time. Yeah. So the first series is, so it took the array1, okay, which is 1, 3.2, 7.5, 8.9, and it used it to create a series. Okay. And then it's also, you can also, instead of using NumPy array, you can use the list also to create a series, which it did. And then finally, what? Yeah.
I hope you're recording.
Yes, I am. Thanks. Thanks. So finally, I took array1 and I changed the index. Okay. I need a different index. So instead of having 0, 1, 2, 3, I want to have A, B, C, D. So I did that using this line. You can add your own index. So I do this. And so if you go down, you will see that it has a series. And the series, so the array is still here, but the series is now ABCD. Instead of 0, 1, 2, 3, it's ABCD. You can create your own Pandas list also. You can create your own Pandas data frame from 2D list. How to do it is here. Okay. You can create a Pandas data frame from a dictionary of lists, which is here. Okay. These two, like I said, I do it for pedagogical reasons. Okay. But most often you will read data from a file. So I'm going to this pass where it says most often you will read data from file. Okay. So there's a file pandas demos.csv, which you need. Okay, so this is why you need to be in the right directory. Okay. If you're not in the right directory, you have to put the path there. So in this case, I just put pandas demo.csv because I'm in the same directory. If I execute it, it has read the data and I can print the top 3 lines. Okay. So the top 3 lines of pandas demo.csv is exactly this. Okay. Module ID, instructor, blah, blah. So if you want, you could use an editor to take a look at what is exactly in pandas demos.csv. It will just be something similar to this, but they are comma separated. So CSV is comma separated variables or values or something. So it's comma separated and you'll see things like that. If you want, I can quickly show you. So with the Pandas demo, you see I have module ID, instructor, TA, enrollment, and all the things are comma separated. The first column, there's no 0, 1, 2, 3. When you create any data frame, this is part of the things that we get from using Pandas. And then it's able to put it in a table and everything like that. So all this information is here. When I do this, so PD, Pandas PD dot read underscore CSV. It will read the CSV file. It will read it into our data. And when I do a head, it will show me, it's showing me the first 3 lines. This is how you can change the labels of rows and columns. Okay, I'm giving it to you as an exercise. It's already there. You can change the label of a row. Okay, you use this index to change the label of a row. So this row the label of the row is 0. The next row, the label is 1. The next row, the label is 2. So what I've done here is to say our data is, one of the methods that you have is rename. So the index, along the index, the one that has index 0, I'm renaming it row 0. Along the columns, the one that has TA, so you see this TA, I'm renaming it teaching assistant. So I'm going to execute this now. So this is the function. Our data does rename. If you like, I can put everything on the same line, but it's not going to fit. Okay, so if you like, I can put everything on the same line, but you have it also. Actually, this is one of the commands you can execute several times and you won't disturb anything. Okay, not all the time you can do that. So I executed it, and then if I do our data.head, you see that TA has changed to teaching assistant, and 0 here has changed to row 0. You can add other indexes or indices also. So I can do, you put a dictionary, so index 0 is row 0. If you like, you can add this one and say 1, you want it to call it row 1. So you can do that also. And if I do this, you see there's row 0, there's row 1, because I changed the name. So you can change the name as you please. Okay. Is everybody on the same page? Okay. The next thing which is very important is you should be able to select data from your data frame. Okay. You should be able to select, say, a particular column or a particular row. This you will need for machine learning. So one of the things, so here I took our data and I'm going to create a new data frame called C, and C contains only the module ID and the instructor name. Okay. So
Actually, to be exact, you're not copying it. You are just
creating another data frame.
No.
Oh.
If you want to create one, you have to use copy, because otherwise you're not creating a copy. It's a link to it.
Oh, so it's just a reference to it. Okay.
It's a bit annoying in Python. You have to pay attention to that. If you really want to create one, you have to use one copy.
Okay. Wow. Interesting. So you mean if I change this C, if you change the
Yeah.
Wow.
That's annoying.
Okay. 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 So I'm going to form another object. I don't want to say create another object. Okay. So I'm getting another object, and the object takes only the column module ID and the column instructor. So how do you do it? You have to create a 2D array. So with this, I'm creating a 2D array. And then when I head the 2D array that I form, I call it C, and then I can head it. Okay, so I do that. So you see now, C just shows me a 2D array that has module ID and instructor, and this does head 3 doesn't mean it has only 3 rows. It means that I'm showing only 3 rows. Okay. Okay. Esther, we'll get to you and tell you what to do soon. You have to navigate to where you have your. You have to download the Day1 and then navigate to where you have your Intro to Python notebook. So another thing you can do is to select, you can use a mask. So I showed you how to do that in the morning. To use a mask, what I did was to create an array. So I took our data and the column module ID, I checked if it's the same as CS101. So module ID, there are 3 lines there that have CS101. So you check if they have CS101. If they have CS101, it will return true. If it doesn't, it will return false. So this array, so when I execute it, you see that the array has just 2 columns. Is either true or false. Okay. It took the index for the rows, and then the first 3 lines are true, the rest are false. The reason is because the first 3 lines are the only lines that contain CS101. So if I do a head here, you see more of it. So only the first 3 lines, 1, 2, 3, contain CS101. The rest contain some other things, CS102 or some other ones. Okay. So only the first row 0, row 1, row 2 contains CS101, so they are true. Okay. The next thing is to use the mask is now I'll take our data, the Pandas data frame. I will put the mask within it. And what this will do is it will link to X4. Okay. And X4 will have only that part of our data where array is true. Okay. So when I execute this, you'll see that only the part where array is true is included. So this one array is true, this array has array true, array true, array true, and these are the only ones that are included. In this case, there are only 3 lines. Here, I didn't put head 3, I just put head. Okay, so you should have shown me the first 5 lines, but the first 5 lines, I mean, head X4 has only 3 lines. Okay, so it shows me all the lines. The same thing I've done, you can do it in one shot. So instead of first creating the array, you can just put the array that you created here, and I head it, and then it will do exactly that. So you create exactly the same thing. So the next thing, which is quite important, is to be able to select using iLock or lock location. Okay. So iLock selects by position. Remember starting from 0.
So I was wrong. It says that it copies.
What?
So I was wrong.
Oh, it copies. Okay. Okay. So if you use iLock or lock, iLock is select by position. Sorry, here I had one. It should be row number starting from 0. Not 1, okay? And then lock selects by row label. So I can do our data.ilock. Again, you see this is a 2-dimensional array. So this will show you not rows 0, but row 1. Okay. So this will print row 1. So it will print row 0, it will print row 1. And then this print /n/n/n will print 3 lines. Okay. And after that, I'm going to use lock. Okay. What lock does is it prints it by label. You can put exactly the label you want. Okay. So the interesting thing is with iLock, you can print row 200. But with lock, you have to know the label of row 200. Okay. So you have to know the label of row 200, okay, and then put the exact label there. If the label has not been changed, it will probably be 200, okay, or 199. If the label has been changed, it will be something else. You have to know exactly what is there. So in this case, I will just call iLock this way, .iLock 1. I print the row 3 rows, sorry, 3 empty lines, and then I'm going to print using this, the row label. So this first one is going to take our data and it's going to print row 1, not row 0. Okay. So row 1 is exactly this one. If you use labels, the first one is 0, this is 1, this is 2. Okay. Not from C, but from the original one, our data. So if you go up, our data is still there on scat. Okay, so this is our data. Actually, I changed this row, but you don't have to change it. You will have row 0 here, and then you have 1 here, 2 here, 3 here, 4, which is fine. So what I'm doing now is I'm going to print this row 1. Okay. So let's see how to do that. So I use iLock to select the row, and then I print it. So this will print row 1. Now this other one will print row 0. So let's do it. So you see, this first one, it printed row 1, not row 0, okay, because Python starts to count from 0. And then this second one prints row 0. But you see, this second case, I use the label for it, row 0. If you like, you can still put lock and just put 0 there. So you print test this one. So I think everybody knows what will happen if you do this. Sorry, please hold on. If you do this, print our data. Dot iLock 0. Okay. What will be the result if I do this? Yeah, if you print if you print the data frame, and the data frame will have exactly the row 0. So it has exactly this. You can call it, you can use lock and call it by label, or you can use iLock and call it by the index. So both of them will give the same result.
I have a question, sir.
Yes. Okay. So I'm asking you these questions. What will this select? So you can try this out yourself. I'll give you a few minutes to select this, to uncomment it out. First, before you uncomment it out, think what results this will give you. Then you can uncomment one of them out and see if your response is correct. Okay, and then you can do it for the next one, and the next one, and the next one. Yes, your question. What's your question?
I said, instead of putting iLog 1, can we write iLog 1:2? I think we still print the same thing.
There's no ratio, is 1 to 2.
Yeah, that's 1 to 2, yeah.
So you can still do that. So let's try that. So you can say I print our data that I lock. I do this, and you are saying I should do 1 to 2.
Yeah.
I think this is going to give me an error.
No.
I think this will give me an error. Yeah, so this prints row 1, yeah. Okay. So when
it's a print 1, yeah.
So this is one of the things. Yeah. So this is one of the things you have to think about. When I write about slicing, when you write 1 to 2, what it does is if you print from index 1 up to, but not including index 2. Okay. So if I do 1 to 5, for instance, it will print from index 1 up to, but not including index 5. Okay. So this will print index 1 up to, but not including index 5. Yeah. Okay. Any questions? Yes.
Can we use this lock with the index instead of label?
Yes. Oh, because lock instead of index. No, lock you have to
instead of label, I put just 1 and it shows.
Let me see. Oh yeah, because the label is important.
That means instead of if it is index or table.
No, because okay, will you put 0 there? Yeah, the 0 doesn't show because you see we already changed the label. Yeah. For row 0, change the label for 0.
That means log for those we already changed it doesn't work.
Yeah,
But if one for those we don't change it to 1.
yeah, because whatever the label is.
It's like
Everybody okay?
When? Because set for we already have but if you put 1 into 1 because you put 1.
Okay, so people have just arrived.
if I don't put 0, I put 1.
If you remove
Yeah.
1, but 0 doesn't work.
Because we don't have to.
Yeah. Have you put that?
So this is but I have to wait.
So for those who just came, I'll send you a link to the file. I'll send you a link. So one by one, please check what this is going to give you. So if you go down, there's all this. So you have to know what each of them will select. So this is how to select parts of a data frame. Okay. So I want to send an email now to.
But each has a different story.
Yeah. So ILOC means index of location. Okay. Thank you. Okay. But if you use ILOC, you access it by index. If you use lock, you access it by the name of the label. So what I need to do now is I need to forward this email. Okay, so I think if our students that just came in, you can check the email. There's a link there that you can use and you can get the. Okay. So this was where we were in the morning. So you can take a look. So you can comment things out, and you can see what this week is. So one thing that is important is you don't have to do slicing. You have the data, you can slice just a master. -1 is the last item. No matter how many items there is. -1 is always the last one. And then -2 is the last one. So you can do that. Okay, so I think so next you can update a data frame. So I started with this data frame. You can add another column to it. So this is what I'll show you now, how to add another column to it. You know, for instance, you can have a column that has the mass, another column that has the volume, and you need a column with the density. So you can do that also. You can, the density is the mass divided by the volume, so you can just add another column to it, or you can divide one column by another column. So you can do that. But in this case, what we will do is we will explicitly add another column. So the data we saw does not have the average CGP of the student. So I'm going to add a column that has the average CGP of the student. So this is the way you add a column. So our data, I'm adding a column that is called average CGPA. And then I just put the data there on one line. So you have the files. So I added a column by saying our data, put another data, put another column called average GPA, and then I populated the list. This is not the only way you can do it. Other ways you can do it is you can use the data you already had. For instance, if you have the mass and the volume, and you need a column with the density is just the mass divided by the volume. So you can divide one column by another column. So you can do that. Okay. So I'm going to execute this just now. Okay. And then after I do that, I'm going to see what our data does head. I mean, what our data contains. So I head it, and you see that magically now there is another column that has the average GPA, and it comes from what I've added. When you create a data frame, there are other methods that the data frame has. Okay, there's a method called isNull, so you should investigate and see what that does. Okay. You did it in the past. Okay. There's a method called sum, so you can add sum of a particular column. There's a method called drop NA. Like if you look here, there's this NAN, okay, and this NAN. NAN typically comes from if there's an empty space there. If there's nothing there, then Pandas will typically interpret that as NAN. So this NAN, when you are doing machine learning, then you have to do what is called cleaning your data. This NAS, you have to decide how you want to treat them. And there are different ways to treat them. One way is to say, since I don't know what this is, I can use the average of this column. Or since I don't know what this is, then this row, the data is bad, I drop the row. I can decide what I want to do. Or since I don't know what this is, I'll use the number that occurs most in this column. I can use it. So different things like that. Okay. So there are different ways to treat data that is missing. So let's actually look at the original data.
Excuse me, sir.
Yes.
Yeah. You added another column called average GPA, which is defined data. That's finite data. What happens in the case where we don't have finite data? Finite data frame. How do you add the data? That's when you don't have a certain number.
Oh, yeah, okay. So usually you create Okay, let's take a case in which let's create it from enrollment and rating. So for instance, I can divide this column by this column. Okay. Enrollment by rating, and then I'll get a new column. Let's call it ERA, enrollment rate per rating. Let's call it EPR. So you can add another column made from the columns you had already. Okay. So it's possible to do that.
Okay.
So the process to do that is similar to this one.
Okay.
So let's quickly do that just now. So I'm going to add an extra column. So let's call it EPR. Gianmarco, I hope I'm right. Is this? I want to divide one column by another column.
Divide one column by another column.
Yeah, enrollment by training.
And you want to create another one from that.
Yeah.
Okay, so you probably need to compute, put again. This you cannot do. I don't think you can. What I would do is create our data. So I would repeat, really close the bracket here and put again our data.
Oh, I see what you mean.
Maybe this works, but I am not aware of that. I can try. Does it work or not?
I don't know. Let me try. Yeah.
Yeah.
I think the easiest thing is to see that I didn't make a mistake in typing the name, enrollment and rating.
So this is a good, a good advice. Try things. If it doesn't work, try to understand why it doesn't work and try to correct. So
yeah.
Here, we can try.
Because in this case, it's just software. If it's hardware like experiments, no.
That's true.
So this is why it's good to do computational work. It's still working. I know.
So then I will do what I told you.
I'm seeing someone. Oh yeah. So let's do that. Our data enrollment divided by our
That should work.
Yeah, I think this should work. No.
Okay, so remove the bracket. Maybe it's nice or like that. Yeah.
Okay, I think you're right. Perfect. Okay, so I took our data enrollment, one column. I divided by our data rating, so it's enrollment per rating. It doesn't make sense, but at least you'll see that you can do it. What I want to do next is I'll now edit. Okay, so I have this, and if you scroll to the right, you see the column I've added, EPR, is there now. And in this case, it doesn't matter how many lines I have, okay? This shows an NaN because it was empty. And of course, it transmits also to when you divide, then it's still NaN. And it's still NaN. So it doesn't matter how many lines I have. So in this case, I've just used data that I already have to create another kind of
column.
Another column. So you can do this. Thank you, Jamaki. So again, if I look in Pandas demo.csv, you see that this line that has Beth, Carol, then there's 2 commas, so it's empty. So you see there's CS101, there's Beth, Carol, then there's 2 commas after, so it's empty. That's why there's an NaN here.
Thank you so much.
Here also, Beth Vera is empty, so there's an NaN there also. This one, Dan, Team, and then after that is empty, so there'll be an NaN there. So those are the ones, the data is not there. It interprets it as not a number. So you see Beth Carroll, and there's not a number. When you do machine learning, you have to clean your data and do something with this. One way is you can just delete all the rows that are deficient. Before you can do that, you have to have a lot of data. Okay? If you don't have a lot of data, maybe it's not wise to do that. One thing you can do is just to use the average of this column. So there's ways to do that in machine learning, or you can use the mode of this column. Okay? So there's ways to do that in machine learning. Okay. Oh. Okay. We are supposed to have a break now. They've not. We're supposed to have a break now. They've not brought the
I think he did.
Because I did okay, yeah.
My question is, supposing I read something else.
He's written this.
The next few
Our data head.
Yeah, that's the same. Head is just the beginning, and what I told you is where the whole thing.
So the next few things that you can do them on.
Otherwise, you won't.
Please make sure you know all of the things.
Thank you so much.
Liquid, never put okay, yeah, please. So please, never put water or liquid. If you pour on it, you keep it here. You type one thing, especially if you have a laptop. If you have a desktop, yes, you can throw it away and go back. But your laptop is very hard. So please, yes, you can take your copy around, or this one. One down here, so that something happens. So, no, nothing happens. The keyboard, the desktop keyboard, you can buy one.
So there is a method.
Yeah, no, it's not here yet.
Everything
No, don't go because the other thing. Okay. Okay. So I show you. So next, I show you a very simple example of matplotlib. How to use matplotlib to plot. I show you a very simple example, very like trivial example. So first, you import the matplotlib. So I have import matplotlib.pyplot as PLC. This is one way to do it. This is not the only way. The other way, I commented it out. So you can try the other way also. So since you have this way, let me comment this out and you see that you get it. Either way works. From matplotlib, import pyplot as PLT. I use PLT because most people do that. Then I import numpy as NP. I create an array in numpy array 1, 2, 3, 4, 5, 6, 7, 8, 9. Then I create another array by taking the square of the first one, multiplying by 0.2 and adding the original array. Remember what I told you about vectorization. This x squared is 1 squared, comma 2 squared, comma 3 squared. So this will form an array. Then I multiply it by 0.2. Some say, why don't I use brackets to make sure nobody gets confused? Don't worry, you won't get confused. Okay, and then I add X to it. Yeah. Oh yeah, you're going to see just now. So I import PyPlot from Matplotlib. There's a module or a class actually called PyPlot. I import it as PLT. So now I'm going to use it to plot. First, I'm going to use it to plot just a scatter plot. I'll comment this out. And then after you do plots.show, it's going to show you. So I do this. So just does the scatter plot. On the vertical axis is Y, on the horizontal axis is X. Then I'm going to do the plot and I'm going to add a line that just joins the point. Unfortunately, this thing is quadratic, so it's going to look like a curve. Okay, smooth curve, but it really is not a smooth curve. It's just straight segment lines that are joining those points. So I do this. The interesting thing is, how do I choose a different color? What? No, this one doesn't. It chooses the same color blue. So you see.
Okay, then there is a way to specify the color. And I'm saying that now I'm using more and more probably rather than.
Oh yeah, okay. So now I do the scatter plot and I also plot a line together with it. So those are two different things. I do them and then I plot. Pandas data frame also has methods that you can call with your data frame also.
You just choose a comment.
Okay.
And then, for instance, if you put R, it's going to be red.
Oh, okay, good. Okay.
Yeah, it's kind of between the quotes.
So the R is going to,
I think so.
yeah, means red. Okay. So I'll do this. Okay, so you see, I have a red line now. Thanks, Jamasa.
Change it here. I think in right color equals to.
So I plotted the line and then, I plotted the points with scatter and then the line. So you can learn how to use it also. It's straightforward. There are many other things you can learn with Matplotlib. This is the basic one. You can plot histograms with Matplotlib. There are people that can do more sophisticated things. Okay?
From what we gave us before, my own thing,
which extension?
from the original thing.
Yeah, to draw the line. So now I put a comma and I put R for red. So that the line is red and the points are blue.
Assuming you did not indicate that it's right.
It will just be blue.
Yes, but what I'm saying is that what you gave us before, that R is not part of it.
Yeah, it wasn't part of it.
And my own is blue line. It's blue line.
Yeah, but it will be blue line.
Okay, the R is just for the
Change it to red. Okay, I think maybe Jim will change it to green or something. Okay.
You can write my color equals, and then I think it's possible to define the colors.
Okay. Okay. So I think before the break comes, we can discuss about files. You can open files. You can read from the file. You can write to different files. Okay. So this is what we'll do next. So the way to open a file, you just put a label, any label you want. Here I use F. Okay. This is the thing that opens the file. This will open a file called water.xyz. The folder I gave to you contains water.xyz. It's a file that contains coordinates of water. And then R here means to read. Okay. So R is for read. You can have W for write. You'll see that later. A for append, meaning the file is already there. Just add more to it. R plus for read and write. Okay. So in this case, I open a file water.xyz using the label F. Okay. The label F will be very important. The label F does not have anything directly to do with the file name water.xyz. Okay. So it's not like you use water.xyz and then F instead of on the left you use water.xyz. No, you just use the label. So each time I do f.readLine, it's going to read one line. I do f.readLine, it's going to read the next line. F.readLine is going to read the fourth line. Okay? And we keep reading each line. So first line, I call it F dot read line. Second line, I call it F dot read line. Yes, they're the same functions, and it looks like the same function call. Well, what happens is this one will read the first line, and then the pointer will move to the beginning of the next one. And then this one will read the second line. And then you can read the third line, the fourth line, that way. So in this case, you can think already that you can have a loop to read all the lines. So I'm going to print the first line. This end means it should end. If you just print first line like that, it's going to automatically put a new line after it. So I don't want you to put a new line after it. That's why I have this end equals in quotes. And then at the end, I close the file. Now that I've closed the file, you can use the label F again if you want to. If you don't close the file, you can use the label F again because then the files are slow. Okay. So if I run this now, it's going to print the first line of water.xyz, and it's going to print the second line. So I do this. Okay. The first line of water.xyz, you can take a look at it if you want, has number of atoms. It has this line exactly, 3 number of atoms. The next line has title, water molecule. So I can open the file for you so that you see here. So the file is here, water.xyz. So this is exactly the file. Number of atoms, title, water molecule. Then there's oxygen, and then the position of oxygen. There's hydrogen, then the position of hydrogen. There's another hydrogen, and then the position also. So these are all there in the file. Okay. I think the next thing we will do is I'll show you how to use a loop to read the file. Okay. So first, I'll open a file called geom.xyz. This is a file that I used in the past that has silicon atoms in it. Okay. So I open the file with the label FR. Okay. You can use any label. Okay. So just use a label, a variable. So I do that. Then I open another one where I want to write something to. So that one I open it with W. Okay. And then what I'll do is this FR, it forms like if you like, you can think of it as a list. I don't know exactly what is in the black box. Okay. But it's an iterable. It's something that you can iterate over. So for line in FR, it's going to do exactly this. Okay, it's going to print line. If you like, instead of calling it line, you can call it for Q in FR. Then here you have to have Q here, and you have to have Q here. Okay, you just put any variable there. So for Q in FR, so line is not something special. It's just for Q or for anything, A or B or anything in FR. So it's going to take this file, geom.xyz. It's going to read it line by line. Okay. If you did not have this line that says A equals Q dot split, if you just print Q, that line, and if you print an end, I mean, this end means you should not create a new line. Yeah, you should just end that one. Because without this, it's going to create a new line. Okay, so I don't want you to create. Actually, it's going to create more than one new line. Already, this one creates goes to the next line, but with end, if you don't put the end there, then you have new lines on there. So if I just do this, it's just going to print, and I'm going to have all this. Now let me comment this out also. Okay. So what it's going to do here is just going to print line by line. So let's do it. I hit return. So you see it's printing line by line. So in the file, geom.xyz, this is exactly what is in it. I don't know how to do it. So I can open the file for you. You'll see that this is what is in it. And it's printing it line by line. It's doing nothing that is interesting. Okay? This is nothing interesting. It's just printing line by line. Okay? So this is what it does. It goes line by line till the end, and it just prints it. Now I want to do something interesting. I want to take each line and the different items on each line, I want to do something with it. So what I'm doing is I do A is Q dot split. Q is like a list, then I split it based on spaces. So this is what it does, it splits it based on spaces. Q now is a text. Okay. I split it based on spaces. Okay. So now this A for this line will contain 4 things. It will contain SI, 0.4, blah, 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 1.9, blah, 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 0.00 for this particular line. This will be what will be A. So there will be A0, which will be silicon, which will be SI. There will be A1, which will be this. There will be A2, which will be this. And there will be A3, which will be this. So this is what this does. So for every line, it will do the split. So there'll be A0, A1, A2. Okay. What I want to do now is that if the first element, sorry, is the first item is SI, then I want to write that whole line. This is what this line is doing. So if A0 is SI, then, okay, so if this, then I want it to do all this, to write this. I'll explain this just now. So when you first read, let's look at the file. When you first read, it's going to read this 3. This 3 is not SI, so it's not going to, if you're going to do the split, this 3 is not SI, so it's not going to write this line. Then it reads the next line, which is equilibrium geometry, blah, blah, blah. A0 will be equilibrium, A1 will be geometry with a colon, A2 will be SI, A3 will be these 2 dashes, A4 will be this one. It's split based on spaces. Okay. Still, A0 is not SI, so it's not going to do anything. It's not going to write this line. Then it reads the next one. Then A0 will be SI, so it's going to write this A0. Okay, I'm doing more than I need. It's going to write this A1. It's going to write this A2, and it's going to write this A3. Okay. So I've done that here. You use this f.write command. This write fw.write expects only 1 string, not 2 strings, not 3 strings. So the way I get around that is the first string, A0, I concatenate it with a space, and I concatenate it with A1. Okay, so it doesn't write everything jammed together. And then I concatenate it with A1, with a space. I concatenate it with A2, then I add a string, which is a space, and A3, and then I put a new line at the end. So it's going to write to a new file called quad only.txt, and that quad only.txt will have just the coordinate. At the end, it's going to close everything. The file I sent to you, I don't know if you, yeah. So once I run this now, it's going to do everything, and then at the end, you can see that there will be a new file. Let me go to another file there. So I go to this Day1. Oh, yeah. So you see that this quad only.txt there. I can open it for you, and it has just silicon and the coordinate, all the way down. I can remove it. I'll show you. Now I removed it, it's no longer there. But when I run the program, it's going to appear there. Okay. So I go there and I run the program. Okay, I run it now. So it does the running. And then I check again, and you'll see that the file is there. So now I do it. You see that created the file again. And you can see what is in the file out. What is in the file is the same. Okay. Because I say it should write, each time it will overwrite. If you want to append, then you use A instead of write. So I think at this point we take a break. Sorry, we take a 9 minutes break. Let's do it this way. Because Anubhav Jain is going to join us exactly 16 days. So you take a break, you take your coffee, and you come here, you sit down. You make sure you don't spill it on your laptop. So you can take a break. The coffee is there.
We are here.
it's my great pleasure to introduce Anubhav Jain, Dr. Anubhav Jain, who got his PhD degree from MIT in the group of Gerd Cedar. And since then, he's got a position as a staff scientist at the Lawrence Berkeley National Laboratory. He's one of the key players of the materials project, and he's, as you can see, he's an associate director. He's been developing a huge amount of important tools such as fireworks. He's been involved in PyMagen, in Atomate, which are used to run workflows to do DFT calculations automatically. And so he's also involved in machine learning to a project where he's using MapMiner, which is creating features for the structures that you can think of. And then he's involved in a project called AutoMapMiner, that can do automatic machine learning for different data sets. And finally, he has been developing something that is called MapBench. And I probably missed a few things that we are still doing also on that. So we look forward to your talk. Thank you very much for being here.
Great, so thank you, Gianmarco, for the introduction. I'm very happy to join you virtually from California. I'm sorry I couldn't be there in person. Today, I want to tell you a little bit about the materials project. This is something that I've been working on for a very long time now, over 10 years since the beginning. And you know, it's grown quite a bit since that time. And I'm happy to tell you a little bit about what it is and how it might be useful to you. So to begin, let me just bring the outline of the talk. So I'll tell you a little bit about what is the Materials Project in case you're unfamiliar with it. I'll tell you a little how it's been used to design new materials. Then I'll also talk about how you can contribute your own data into Materials Project if you'd like, and also how Materials Project is used to benchmark machine learning algorithms. And then finally, I'll talk a little bit about the software tools that Gianmarco mentioned in the introduction. So in terms of what is the Materials Project, the Materials Project is now many things, but the real core, the basis of it is a database of calculated materials properties, as well as crystal structures, typically of inorganic materials. So the website for Materials Project is materialsproject.org. It now has data on about 150,000 different chemical compositions and crystal structures. This includes information such as the electronic structure, so the band structure, band gaps, electronic properties. It includes phonon and thermal properties, not for every material, but for many of the materials. Elastic and mechanical properties, so how hard, soft it is, bulk modulus, these sorts of things. And many other properties, magnetic, ferroelectric, piezoelectric, etc. And the way that this data set has been created is we actually ran hundreds of millions of CPU hours worth of computing on various supercomputing centers. So this has been millions of US dollars worth of computing that was used to run these simulations on all of these different materials and then put them up on a database so that you could actually download the data. Over time, we've been growing the data set. So we released the Materials Project in the year 2011. At that time, we mainly released a bunch of crystal structures as well as basic properties like battery properties and thermodynamic properties. But over time, we've been expanding the size of the database. So this is a number of database entries. And we've been involving more and more materials in the database. We've started to add a few molecules to the database as well. And we've also been increasing what types of properties are available for each material. So today, for example, you not only get energetic properties of the materials, you also get these electronic properties, these phonon and thermal properties, temperature dependent properties, calculated spectra, elastic properties, etc. So, these days, quite a bit of data is available. And this data has been used by people for many, many applications. These days, actually, one of the big reasons people go to the Materials Project is for data sets for machine learning. To do machine learning, as you know, you need lots of data. You need to be able to train on a data set. And so people use this data as one resource for that. In addition to the data sets themselves on the Materials Project website, there are many different what we call apps. So these are different types of tools that you can use. So instead of just looking at the data entry by entry and looking at one material at a time and its properties, you can actually do things like make phase stability diagrams. So you can see in a certain chemical space, what are the stable types of compositions, what types of decompositions occur. There are tools for specific technologies, like there's the Battery Explorer that can tell you if you were to use these materials in a battery electrode, what would the voltages be? Would it release oxygen, which is bad for batteries? And there are also tools for evaluating things like aqueous stability, like will this material be stable in water? We recently used this last tool in one of our own projects because we were looking for materials for water purification, catalysts that we can use and put in water, and it will actually remove harmful nitrate from water and convert it to nitrogen. And so this tool was helpful for us to evaluate, which of the materials in the materials project are actually water stable. In addition to the data and also the apps on the website, there are a lot of offline tools. These are typically Python-based tools that you can download and use for your own purposes on your computer. These include codes like PyMatGen, Custodian, Automate, Fireworks, and MapMiner. Jean-Marco mentioned all of these. I'll be going through these codes in a little bit more detail later in the talk, so I won't talk much about them right now. One that I won't talk about today really is called MapMiner. This is a tool that will let you take a data set, like for example, materials project, add various descriptors to your data. So if you have a chemical composition, you can get descriptors like average melting point, or if you have structures, you can get various structure-based descriptors, and then you can use that to train your machine learning algorithm. Unfortunately, I won't talk about that today, but certainly we can have a discussion about it some other time. At this point, materials project is used quite heavily by the research community, including all over the world. And so we now have actually over 250,000 registered users as of now. And we get many more users every day. And certainly this has become a worldwide resource and a worldwide collaboration. Most of our users are actually from student or academia, so typically students or professors. We have about 10% of our users that are from industry. So there's certainly a lot of companies around the world that use Materials Project, sometimes saying that they were able to do research that originally took them weeks in the past, now takes them about 15 minutes or so. So certainly this can be used to accelerate various industrial design efforts as well. So now that I've given you an overview of Materials Project, I'd just like to talk a little bit about applications to how you can design materials with this resource. Historically, the Materials Project started off in battery research. So even before we officially deployed Materials Project in the year 2011, back in the year 2008 and 2009, we were doing some research internally where we were trying to use computers to design new types of materials for lithium-ion batteries. And what we were doing was trying to screen through in the computer many tens of thousands of compositions for use as battery cathode materials. So you can see over the course of a couple of years, we screened about 20,000 different materials in the computer, different types of materials like nitrates and carbonates, et cetera. And then we were able to look through the database of calculations and identify certain materials that looked to be good for lithium-ion battery applications. So there were 3 of these, for example, that we were able to patent and show that they worked well in the experimental lab as well. And some of these were made for the first time based on our calculations. Other ones were actually materials that were known to exist, but then we were able to show that they are actually good battery materials as well. Since then, others have also used the Materials Project to identify battery materials. So this is a much more recent paper from 2020 by a group that's outside of Materials Project. And they were looking at using this database to design new cathode coating materials. So you have your battery cathode material. This is the thing that accepts and releases lithium on charge or discharge. But then you want to coat it to get extra stability versus the electrolyte. And so you need a coating material that is compatible with the cathode, but also has phase stability, electrochemical stability, and also good lithium ionic conductivity. And so what this research group did was they actually started with the Materials Project database. They wanted to target fluoride, so lithium metal fluoride. So they identified everything in our database that had that, about 920 materials. And then they used the various filters in our applications to narrow that down to about 20 different candidates. So you can clearly see how you can go from a large pool to a small number of candidate materials just using the website itself, essentially. And then once they had the 20 candidates, they did a few of their own calculations on conductivity and stability, and were able to identify a few candidates that they think might actually be very good lithium-ion battery cathode coatings. In addition, people have used machine learning, materials project for machine learning, as I mentioned. So here's another project from outside of materials project, where they were able to actually take the data from materials project. So they retrieved data from the materials project database using one of our software tools called PyMatGen, and they were able to get 4,860 different materials and their battery properties. So here's, for example, an example of an entry where they have a battery material in the charge and discharge state. This is a sodium-ion battery. Versus lithium ion. And then they actually were able to look at the voltage as well as the volume change upon intercalation. And they were able to train a machine learning model that predicted these values. You know, the materials project can be used for direct material screening. It can also be used to train machine learning models. Apart from batteries, materials project has been used to design many new materials in lots of different fields. And so I don't have time today to go through all of these examples, but certainly materials project has been used for thermoelectric materials. These are materials that will convert waste heat to energy. So if you have, for example, automotive exhaust that's at high temperature versus the ambient air, or industrial waste heat for power generation, you can have a thermoelectric material and it will convert that heat to electricity. And so we're certainly looking for materials that have very high conversion efficiency, can turn a little bit of heat into a lot of electricity. And so materials project was able to identify new compositions that have this property. Materials projects have also been used for phosphor materials. So as we replace typical incandescent light bulbs with LED light bulbs, we need efficient phosphor materials that have good color properties that will give us good replacements to the standard light bulbs. And so materials project was used to actually help predict a completely new chemical composition and show that it had good light emission properties as well. In addition to these examples, I can't go through all of these in detail with the time that we have, but it's been used to identify materials for carbon capture, transparent conducting materials, piezoelectric materials, which convert mechanical pressure into electrical charge, magnetocaloric materials, photocatalysts, and electride materials. And these are all cases where the materials were identified in the computer, but then they were also made in the lab and their properties were tested in the experimental lab as well. So if you're interested in more examples of how people have come up with materials in the computer and then gone on to show that those materials actually work well in the experimental lab as well, we've written a review paper about it. So you can see the link here. And then, the slides for this talk, by the way, are on our group website. I'll put the link at the end of this talk. And so if you want to go back to any of the links that are in this presentation, you can see them online. Okay, so now that I've talked about the materials project as well as its applications to functional materials design, I want to tell you a little bit about a new feature that we have, which is community data contributions. This is a way for anyone in the world essentially to be able to contribute their own data and have it show up on the materials project website. And so one reason we started this is because we felt that the materials project right now has a lot of computational data, but people are also interested in other types of data. They're interested in experimental data. They're interested in other types of computational data that maybe we don't calculate, higher accuracy calculations or other types of calculations we don't typically do, like molecular dynamics. And so we wanted to have a way for that type of data to show up in the database as well. And so one thing that's nice about materials project these days is that it now has high visibility by search engines. So if you go to, for example, Google, and you were to search for a chemical composition, in this case, molybdenum diselenide, this is a relatively common material. You can see that the third link is actually the materials project webpage. And so if you had information about this material and you were to put it on materials project, there's a high likelihood that somebody that's searching for this material would be able to find your data set because materials project was one of the first links, so they'll click it, and then if it shows up on this web page, then they'll see your data. So what we wanted to do was then create a feature where people could in fact add their own data to materials project. So the way that it works is something like Google or the existing community of people that use the materials project will go to a particular materials webpage. So in this case, this is molybdenum diselenide and materials project. And there's a section of the data. So most of the data is what we've calculated, but there's a section of the data called user contributions. And the user contribution section allows anybody to actually enter their own data into the materials project. This is a data set that was contributed, for example, by Denmark Technical University. They had more accurate electronic band gaps than what was on materials project. They did more accurate calculations on these materials. And so they were able to report these band gaps that are with this GLLB-SC functional. And now people can actually see that on materials project. Here's another data set. This is from Francesco Ricci, who was actually in John Marco's group at the time. And so they were able to calculate a whole bunch of carrier transport properties. So this includes things like electronic conductivity, electronic contribution to thermal conductivity, Seebeck coefficient, and a lot of things important to thermoelectric materials, as I mentioned previously. And this is data that was not available on the materials project previously. So they were able to calculate this entire data set and then contribute it to the materials project. And now people can search and see it on the materials project as well. So when you do contribute data to the materials project, there's a link. And then when you click the link, it'll actually cite your paper if you've published a paper about your methods. And then you can also have a data set page where you present your entire data set and there's visualizations about your data set, et cetera, so, and filters and things. So if you're interested in contributing data, certainly would encourage you to check out this MP Contribs tool. Right now, there's about 27 different public projects. So, 27 distinct types of data sets that have been contributed to this MP Contribs tool. So there's been about 500,000, so 500,000 different crystal structures that have been contributed, about 385,000 different tables of data, and then about 500,000 additional attachments and things that have been contributed. We've also been connecting with some of the experimental light sources. And so data that comes out of the light sources is now also being piped into the materials project. We're also doing two types of data sets. We're doing standard data sets. This is the type of thing that anybody can contribute. And then we're also developing some enhanced data sets. So these are data sets with visualizations and exploration tools and things that we're developing around user data sets. For example, recently we had a group contribute millions of data points on catalysis and catalytic properties of materials, and then we actually developed some visualizations for them. One new part of this MP Contribs tool is called MathBench. It's about machine learning, and so I'll talk a little bit about MathBench as well in the next part of the talk. So MP Contribs now is open for contributions, so you can apply to contribute your data set, and we'll work with you to disseminate it. Just to preface this is really designed for smaller data sets. So if you have some materials like chemical compositions and some properties that you've measured, or maybe some small spectra or things, this is really for like megabytes to gigabytes of data. If you have very large data files, so if you have terabytes of data, we would suggest you actually try other repositories. So for example, Nomad, which you might have heard about already, or you'll be hearing about later in this workshop. Nomad will allow you to contribute very, very large data sets if that's what you're looking for. And the other thing that's really useful about MP Contribs is you can link to compositions that are in materials project. So if you're contributing data on a material that already exists in materials project, that's probably the best use case of this tool. If you're contributing data on materials that are not in materials project, they won't be connected to the rest of the website. And so it's less of less interesting in that sense. So if you're interested, you can check out mpcontribs.org, and then you can see if you would like to contribute your own data sets. So I mentioned also that part of MP Contribs is about machine learning. This is a new capability that we've been working on for the last few months or so, and this is called MathBench, and it's about really benchmarking machine learning algorithms. As you learn about in this conference or in this workshop, there are many different machine learning algorithms out there. There are many different tools and things in order to predict properties of materials. And it can be difficult to know, if you develop your own machine learning algorithms, how well is it working? Is it working better than what exists, et cetera? So what we did is we contributed 13 different data sets. These are the different 13 data sets. And these are intended to be tests of machine learning algorithms, meaning that we want to run machine learning algorithms on these 13 different data sets, determine how well they do. And the ones that do the best, we can call, the current state of the art for machine learning. So these data sets were designed, first of all, because they have available chemical compositions and crystal structures for you to train on, but also they were designed to have many different numbers of samples. So some of these are small data sets with only 300 data points, and some of these are large data sets with over 100,000 different data points. And so you can test whether your machine learning algorithms work well for small data sets, and you can test whether your algorithms work well for large data sets. We also chose many different types of materials problems. There's ones about electronic properties like metallicity and bandgap, but then there are also tests for mechanical properties like bulk modulus and shear modulus, optical properties like refractive index, and thermal properties like phonon peak locations. So you can really see whether your machine learning algorithms tends to work well for certain types of materials properties versus others. So in addition to the MapBench having these data sets available, so you can download the data sets, you can split them up into training and test sets, and then you can train your machine learning algorithms on those data sets. MapBench also includes some software tools, so you can download the MapBench software library, and it will standardize the test splits according to something called nested cross-validation. This is a very trustworthy way of doing your cross-validation metric. And then you can also use this MapBench software library to submit the results of your machine learning algorithm to an online leaderboard. And the leaderboard will actually report how well your machine learning algorithm is doing and compare it to the other machine learning algorithms that have been submitted. So this is what the leaderboard looks like right now. It's on mapbench.materialsproject.org. What's on the left here is actually just the 13 data sets that I mentioned previously, the different types of materials problems and data sets that you can train your machine learning algorithm on, and how many entries are in each of those data sets. So again, ranging from 300 to over 130,000 materials. This algorithm section says which is the best machine learning algorithm on that data set so far that we've gotten. And so you can see for some of these, you have more typical things, typical algorithms like AutoMapMiner. For other ones, you have more transformer-based and more recent algorithms like CrabNet. And for other ones, we have things like graph networks like CGCNN. This graph to the right is essentially the same data as the table. You can see the different data sets. These are the data sets with the smallest number of samples and the largest number of samples on the right. The lower the score, the better the algorithm, the lower the error. And you can see that there's different algorithms like CGCNN, CrabNet, et cetera. And you can see which of these algorithms do the best on these various problems. So over time, we expect more and more algorithms, machine learning algorithms, to be tested. And then we'll have a report as to which are the best machine learning algorithms for various problems. I think pretty soon we want to also add another algorithm. So Jean-Marco has been working on something called ModNet that's been recently published. I think ModNet has been shown to do pretty well on both small and large data sets. So again, over time, this list will update and we'll see how these improvements to various algorithms will change over time.
On the website, it's already there, but
oh yeah, I'm sorry, this screenshot is probably old. So yeah, on the website, I think the ModNet one is already there. You're right, Jean-Marco, yeah. Okay, so moving on to the last part, I think we should have plenty of time for questions, but so the last part should be using the software tools. So in addition to the data itself, we've also released a bunch of software tools for doing these simulations. You saw some of the demos, I think, previously on how to set them up. But we have software tools for generating material, so generating the geometry files where you specify all the atom locations and things. Once you have the geometry of your material, there's also codes for doing the simulation procedure. So if you want to know the elastic constant, how do you set up the series of calculations that gives you the elastic constant of the material? Or if you have a certain material, you want to know its band gap, what calculations do you do to get the band gap, et cetera. So there's codes to help you get those simulation parameters. And then there's also codes to help you execute those simulations on various supercomputing centers. And then finally, once the calculations have been completed, there's codes to help you with the data analysis and insights and things. So these are just the names of the codes that help you with the various things. I'll step through them in detail next, but PyMatGen is a code that helps you with materials generation. Atomate and PyMatGen help you with the simulation procedure. There's a code called Fireworks along with Custodian that helps you with executing the calculations, and then many of the codes can help you with the data analysis. So starting with the materials generation, how do you actually set up the materials that you would like? So we have a tool called PyMatGen that helps you with that. The code is on GitHub. I don't know if I put the link here, but you can just search for the word PyMatGen. And it can help you generate crystal structures, molecules, and systems like surfaces and interfaces and things. So for example, one common thing that people will do is to take a material from the materials project and then use PyMatGen to create a surface geometry where there's a big vacuum space and there's also a surface space. They might also take two materials from materials project and create an interface with PyMatGen. There are many other tools as well. So for example, it can take a disordered structure. In this case, a material where the black atoms might represent like 30% oxygen and 70% fluorine. And you can't do a calculation when an atom is 30% oxygen and 70% fluorine. So it can help convert some of the, some of the black atoms to oxygen and some of them to fluorine to create an ordered structure that you can actually calculate. It has tools, for example, if you give it a material, it can find interstitial sites. So places that you can place additional atoms. I already mentioned surface and slab generation. I can do structure matching to tell you whether certain materials are essentially the same framework. And it can also help you get structures from materials project. So once you have your material, whether it's an interface or a single bulk material or some other type of thing that you would like to simulate, the next part of the process is to come up with the simulation procedure. What are the settings and things of your density functional theory code that allow you to get the properties that you would like. So for this purpose, we have a library called Atomate. So Atomate is something that we developed to work with a couple of different DFT codes. So VAST is what we typically use for solid DFT calculations. We use QChem for molecular calculations, and then we use a code called FEF for some spectra calculations. And so Atomate works with these various DFT calculators in order to calculate various properties of materials and to come up with the sequence of calculations that you need. I will say that in order to use Atomate, you do need to have access to these other codes. If you don't have access to the other codes, you can't really use Atomate itself because it relies on these calculators to do its actual DFT calculations or other theory calculations. So once you have these codes, you can use Atomate to actually do many different types of calculations very simply for your material. You can essentially give it your materials geometry and say, I would like to do an elastic tensor calculation, or I would like to do a ferroelectric calculation, or I'd like to do some magnetic properties or thermal expansion properties, etc. And then Atomate will actually set up a sequence of calculations, a calculation workflow that will actually do all the specific calculations with the specific settings that you need in order to obtain the property that you would like. So here's just a little bit more detail about how Atomate works. The input that you give it is a structure or a geometry. In this case, this is what it looks like. And then you can also give it some optional parameters, like what sorts of calculation settings would you like to use if you don't want to use default settings? Where would you like the database file? What database would you like the output results to go into once the calculations are finished, etc. But once you give it the inputs, it will actually create a bunch of calculations, in this case, a series of 4 separate DFT calculations that will help you optimize the structure, optimize the geometric structure, optimize the electronic structure, and then do various high K-point calculations in order to give you the band structure, the electronic band structure. And within each of these calculations, it will write the input files for you. It will run the code for you. It will store the results in a database and pass any needed information to the next calculation. So it will, these codes can be a little bit tricky to use in the beginning, but once you get the hang of it, it actually becomes very smooth to run many different types of properties of materials. So once you actually have the material and then also the sequence of calculations that you want to run on that material, we need to actually execute them on the supercomputing centers. So for that purpose, we have a code called Fireworks. This actually allows you to execute the workflows either locally on your own system, if you have the DFT code locally on your computer, or more typically, the codes are at supercomputing centers, so you can execute these calculations at the supercomputing centers. It works with many different queuing centers that are typically available at these supercomputing centers. And then there's also some like cloud-based computing that people have also developed for Fireworks, so you can run on the cloud as well. If you use the Fireworks code, you can actually submit millions of calculations on the supercomputing centers. It doesn't have to be just one or two, it can be millions, literally. And it will have a dashboard of all the calculations, how many are currently running, how many have been completed, how many have failed, etc. And so you can get a report of how many jobs have been completed in the last year, or the last 30 minutes, etc. And then you can look at every specific workflow and see, okay, the first 3 steps of my calculations have finished, and the last step is still waiting to run. And then for each of the calculations, there's detailed information about the database, about which of the supercomputers the calculation ran on, what time did it start running, what directory is the calculation located in, what were the outputs of the calculation, and then when was it queued, etc. So there's a lot of information in the database that gets automatically stored about each calculation. So finally, once you've done the geometry, you've done the procedure for the calculation, you've actually executed the calculations, there's the data analysis part. And I won't talk in much detail about it, but you can use the PyMatGen code again, and you can generate things like phase diagrams and Porbet diagrams, diffusivity estimates and things from these various codes. So if you'd like to get started in using these various codes, there's many different resources that are available. Each of the various codes that I mentioned, PyMatGen, Fireworks, Atomate, they each have papers associated with them. Those are good for a general overview of what the code does, kind of like I'm saying in this talk, but they're not very practical. They're not very hands-on. The papers don't give you code examples or exactly what you need to type in order to make them work. So I wouldn't really recommend those as the beginning point, unless you're just trying to get a sense for what the codes do. We also have in Materials Project workshops. So we have yearly workshops that are in person. They've been virtual the last couple of years, but typically they're in person, where you can attend the workshops, and then we'll give tutorials about how to use the various codes. Now, the workshops are not possible for everybody to always attend, but we actually have the workshops, the previous workshop materials all online as well. So you can go online and you can see the videos and recordings of all the previous workshops and how to use the tools. So this is a good way to get started, because then you can just watch a video about the various tools and how they work. And so I'll provide a link to the workshops in a minute. In addition to the videos, we actually have documentation for all the codes. So this is web documentation. The documentation tends to be very comprehensive. It has all the features of the codes and everything, but you probably need some experience with the codes to use them, because they can be a little confusing. And then finally, we have help channels, so online help channels, where if you've already started and you run into a certain problem, the help channels can help with that. So if you're interested in the workshop materials and the videos where you can watch the YouTube videos and see how to use some of these tools, they're available at workshop.materialsproject.org. And then the workshop will have both videos. They'll also have Jupyter notebooks and code examples and things on GitHub, where you can actually download the notebooks and run the notebooks yourself. And you can see the code examples in addition to the videos materials. The videos are available on that link. They're also available on the YouTube webpage for Materials Project. So you can search for Materials Project on YouTube, and you'll see a bunch of videos. We have lectures from scientists around the world. We also have tutorials and things on our YouTube page, and then it will tell you how to things like the videos will tell you things like how to run Atomate workflows, view the status of your jobs, and submit to HPC. So again, if you're interested in the tools and you'd like to get started, this is probably one of the best places to start. There's also documentation for all the codes. As I mentioned, the documentation is much more comprehensive, but it is a little bit more difficult to read and to get used to. So, I put the links for the various documentation for the various tools. So if you want to learn everything, I would probably suggest starting with Atomate because it uses all the other tools, and that will allow you to start running some calculations. And then finally, we have a help list. So there's a help forum for each of the codes. So there's a help forum for materials project itself if you have trouble with the website, et cetera. Then we also have a help list for the various codes. So MapMiner, which I didn't really talk about, but has machine learning tools, PyMatGen, Atomate, Fireworks, et cetera. And now there's also on matsci.org, it's not just materials project. There's a lot of other separate projects that have decided to use this as a help forum as well. So projects like LAMPS, which does molecular dynamics, ASC, which like PyMatGen helps you create crystal models and also run calculations. Nomad, which is another database of materials properties separate from materials project. We're all kind of unifying around this matsci. Even though we're separate projects, we're kind of unifying around this one help list that contains a lot of material science knowledge and a lot of material science help. Okay, so just to conclude the presentation, the Materials Project is a free resource that has data and tools to help perform research and development of new materials. I gave examples in batteries and a few other things like thermoelectrics about how new materials could be discovered with these databases. The number of examples of people designing new materials with machine learning, with calculations, it keeps increasing over time, and we're seeing more and more examples where people are designing new chemical compositions inside a computer, things that are interesting for clean energy, clean water, et cetera. And people are actually making those materials in the lab and showing that they work. And then finally, if we unify as a community, we can help get machine learning algorithms tested. We can develop much better machine learning models as a community. We can also share data sets amongst each other and make sure that whatever knowledge is gained in one place gets disseminated to other places as well. And so we can really work together even more, I think, using some of these tools in order to really have a unified push towards better machine learning as well as better materials design. So with that, let me just thank a few additional people. So Christine Pearson is the director of Materials Project. She has been, she started Materials Project along with a few other people. And then also Matt Horton and Patrick Huck are staff developers on Materials Project. They've been doing a lot of the software development on this for the last few years. And some of the features that I talked about, like MP contribs, were really led by them. So with that, let me just say that the slides are already, all the slides that I just presented, they're already uploaded to our group website. So if you just go to this last link, there's a button called slides, and then you'll see the presentation and all the other links that I presented during the talk. So with that, let me end and see if there are any additional questions for me to answer. Thank you.
Questions?
I have a question.
Can you hear?
So yeah, Anubhav, can you hear?
I can hear a little bit, but maybe if Jean-Marc could also repeat the questions afterwards, it might help me. Yep.
Yeah, so thank you for the presentation. My question is this: the band gap of the materials you have on materials project is from PBE, which we all know does not work for band gaps. So so how easy it is to do calculations with the modified Becker-Johnson LDA functional on the same compounds and have the more accurate band gap?
So I can repeat the question if you didn't get it. Anubhav, it's about the band gap, the fact that the band gap that are reported on the materials project are PBE, and so they are underestimated. And so the question of Omololu is how difficult would it be to do, for instance, modified Becker-Johnson calculations to have better band gaps?
Great, yeah, it's a great question. And it actually confuses the experimentalists a lot because when they look up the band gaps on materials project for like silicon or something, they see the wrong band gap and they say, what is going on with this database? So it's a great question to ask about the PBE band gaps and what can be done to make them more in line with the experimental band gaps. As you know, there are many competing functionals for how to get the correct band gap. The modified Beck-Johnson modified Beck-Johnson is one of the most popular ones, but there's also, you can use hybrid functionals. I mentioned previously this GLB, SC functional, et cetera, for doing the band gaps. So our opinion in materials project, and this is a topic that people will argue about forever as to what is the best way to get band gaps. But I would say our opinion is we actually prefer hybrid functionals for the most part, because not only do you get a better band gap, but you actually get other properties like the energies and things better. So we actually did start computing a bunch of things with hybrid functionals, but then it quickly became very expensive. Our current strategy, I would say, is to actually leverage the community more. And so I mentioned in the MP Contrib slide that there was a group at Denmark that was actually contributing band gaps for many materials. I think at this point, maybe several thousand materials with a GLLB SC functional. And so again, this gives results that are much more in line with experimental data than PBE does. So it's always a little bit of a decision as to which functionals we're going to use. Are we going to do it over everything, etc. And then we also were thinking at one point to use GW calculations, but then those would be even more expensive. We've also debated using machine learning to just fix the PBE calculations and give a machine learning band gap. So machine learning adjusted band gap to the PBE, for example. So I think all of those are viable strategies, and we haven't really deployed any of them yet, except for having the users be able to contribute better band gaps.
So the ones that are reported are pure PB or machine learning adjusted?
So the ones that are reported on the website are pure PBE. There is no machine learning adjusted on the website, right?
That's correct. That's correct. Yeah. So we've debated having fitting a machine learning model on top of that, and then also allowing users to search on that if they would like. But we haven't done that yet. And so right now, if you go on our website, all you see is the pure PBE band gaps.
Thank you. Yes.
In the presentation, you said that automate
yeah.
uses only maps.
Yes.
So it means if I want to use open source software like CSS, how do I go about that?
Okay, so the question is about the fact that Automate is only interfaced with VASP. And so if we want to use open source software, how do we go with that?
Great. So that's also a great question. So we've been working actually with Jean-Marco to try to get at least Abinet integrated into Automate. So we're working on a new version of Automate called Automate 2. And we've been working with Jean-Marco's group to actually have Automate 2 also work with Abinet. So we're hopeful that, in the next year or so, we'll actually have at least Abinet as an open source option that you can use when you use Automate. That is hopefully coming. The other codes like Siesta, Quantum Espresso, these sorts of things, we don't have any plans right now to integrate any of those other options into Automate. So you do have to use the calculators that are supported by Automate. There is another code called ASC. You might be familiar with ASC already. But they actually support a wider variety of calculators than Automate does. So there's advantages to ASC. I think ASC is much more flexible in terms of the types of DFT calculators you can use. But Automate maybe has more workflows available, a little bit more powerful database entries and things like that that also have advantages to Automate. So I would say, if you're interested in open source, Automate 2 should have Abinet as an option for an open source DFT calculator. But if you're interested in the other DFT calculators, I don't think they're coming to Automate anytime soon. ASC might be an option to look into in that case.
If I may add, Anubhav, I mean, if the discussions we have with the people from both ASC and AIDA work out correctly regarding job flows, then you might have workflows for a Quantum Espresso also with that.
Yeah, thank you for reminding me. So yes, we're also working on making Automate 2 compatible with a more generic workflow infrastructure called JobFlow, and so this would actually allow greater interoperability between ASC and some of the tools that we've developed as well. So we're working on integrating even further in the future as well. So thank you, Jean-Marco.
Another question?
The other question is how reliable is the surface you generate using fine margin? Like
To surface.
yes, surfaces. If you want to do calculations on surfaces, how reliable? How do you ensure that the surface you're actually working on is the correct one?
So the question is, how reliable are the surfaces that are generated through Pymagen? And yeah, so that's it.
Great. So it's a complex question. There's two types of reliability. Is the algorithm performing properly and giving you the surface that you asked for? And then then the second question is the surface that you asked for the correct surface that is actually going on in the physical system? So, I think the first question is, if you ask for a 111 surface of iron with, 8 angstroms of vacuum or something, the Pymagen code can reliably give you that surface and then you can model it. Now, in terms of whether it's the correct surface and whether you're getting the right properties for your physical system, that can be complicated because, in some cases you have surface reconstructions happening. And if you haven't, taken those into account either in your geometry optimization or when you've created the initial geometry, you won't see that in your calculation. So you have to think about, are there surface reconstructions that might occur? This is particularly important if you have a charged surface where there's what's called tasker reconstructions, and Pymagen can actually help you create these like tasker reconstructions that help you create charged surfaces. In addition, when you have a surface, there's usually an interface either with, often with like a liquid or something. And then there's, some kind of whether it's a liquid or a gas, there's often some kind of a surface layer on top of your surface. So in between your surface and whatever medium you have, there's some kind of a passivation layer, some kind of interface layer, et cetera. And again, Pymagen won't tell you about those things. You have to kind of think of them, you have to try them and model them themselves. So I would say, the algorithmic accuracy, getting what you asked for, that is pretty, solved. In terms of the physical accuracy, whether it is actually what's going on in your system, that's still a very complicated problem, requires probably a good amount of research, very good PhD topics, I think, in terms of trying to get accurate surface calculations and making sure they're reliable.
One more question, yes, go ahead.
Yes, so do you capture structures like zeolite?
So do you capture structures like zeolite on the materials project?
Yeah, so I mean, we do have some zeolites from DFT. We also have what's called a MOF explorer. So this is metal organic frameworks, but they also have zeolites as well. And so those were calculated more with molecular dynamics because some of the zeolite structures can be a bit larger and difficult to calculate with DFT. And so the MOF Explorer app, there's one of the apps on Materials Project called MOF Explorer, has done a bunch of gas absorption calculations with zeolites as well as metal oxide frameworks. And so you can see, for the different zeolite structures, as well as MOF structures, how much gas absorption you might be able to fit into, certain of these framework structures. So some zeolites are there, others are not. And again, because these are larger structures, other techniques like molecular dynamics and things might be relevant there.
Thank you. Is there any other question from the audience here? Just one more there, yeah.
Doctors say that the material project is used for a smaller data set. Does it mean that the material project is more for electronic structural calculation and not molecular dynamics? What is the range of a file that you have to limit for material project?
So I'm not sure that I got the beginning. So who said that it's for small data?
Material project is used for smaller data set.
Who said that?
Oh, the contributes.
Oh, okay.
If you have larger data set, you should go to normal.
Ah, yeah, okay.
Is that what you mean?
Yeah.
Okay, so the question.
Sorry, could you?
Yeah, I'm gonna say it. So you mentioned that for the MP contribs, it was intended more for small data sets. And so the question is more about what is the, let's say, the scope of the things that you would like to have on MP contribs?
Yes, it's more used for electronic structural simulation and not for molecular dynamics. And what is the range of the data that you can put in the file for the material structure?
So it's MP contribs is files that you are contributing to the materials project. So the question is about the kind of things that people can contribute. Should they contribute also electronic structure? I think that you gave the example of the GLLB from the people in Denmark. and or molecular dynamics?
Great. Yeah, it's a great question. Let me try to clarify for empty contribs. So, for example, let's take the example of the GLLB SC data set. The calculations have many outputs associated with them. There's the raw band gaps and the raw things like that. And so you can see this is a small portion of the data set, which is the actual band gaps themselves, the delta E, concham, and 3P, et cetera. And then you can see for this carrier data set also that there's small amounts of data here. This is the data that you would want to search on, and this is the data that you might want to display very directly to a user, and that will go directly to MP contribs. Now, in addition, these calculations will probably have things like wave function files, charge density files, et cetera. These are things that the user would not really search on. These are things that we probably wouldn't visualize for the user on the database itself. So these are things that are, and also larger files, so at least a gigabyte per file. These are things that we wouldn't necessarily store with MP contribs. The gigabyte is probably about the edge of, so gigabyte times, 1,000 materials becomes 1,000 gigabytes or terabytes. So, that comes like, on the edge of what we would store. So instead of that, what we would do is we would probably say, the core data, the thing that people want to see, like the, the band gaps and things, you should submit that via MP contribs. And then the things like the wave functions, the charge cars, these larger files, these are things that you might want to store with Nomad and then link to materials project. So if you were to have a molecular dynamics simulation, for example, let's say from the molecular dynamics, you've extracted a diffusivity number for a material, a self-diffusivity or something. You would ideally want to submit the diffusivity numbers or the things that people really want from your molecular dynamics to materials project through MP contribs. So people can search and say, what are the highest diffusivity materials? What are the lowest diffusivity materials, et cetera? And they'll be able to search that on the database. But then the full trajectory files, if those are very large trajectories, these are things that people wouldn't be browsing or searching on directly, those might be contributed, those files might be contributed to Nomad and then linked through Materials Project. In fact, Materials Project itself, disseminates charge car files and wave function files, for example, but we don't disseminate it ourselves. We actually submit those files to Nomad ourselves, and then people can actually download those files through Nomad. So hopefully that kind of tells you the distinction about, certainly we're open to all sorts of data, but the things that people really want to search on, the things that people really want to see, those are the parts or plot. Those are the things that we would really want to put on MP contribs. And then the raw files that are for reference, that are large, those maybe require separate analysis. Those we would put on another database.
Thank you. Is there any question online by any chance?
Yes.
Sorry, I have some more practical questions. So I hope material project will be there forever, not that after a while. I mean, is the funding continuing, and like where is the database? Is it stored so that you can always access it, or maybe after 10 years the project ends and then you have to start looking elsewhere? So that's one question. Wait, sorry, please. Then one other question is the data from MP contribs, is it curated or not? Like some student can just submit some poor data, and would this still be there, or do you curate the data? Thanks.
Great. So the first question about the longevity of Materials Project and, will it be there forever? I wish we knew for sure that it would be there forever, but it's been going for the last 10 years. And over the course of the 10 years, the funding has become from more stable sources, I would say. So for example, as of 10 years ago, first we had to get the initial funding, which was very difficult. And then as of 5 years ago, we had to always keep renewing the Materials Project. We had to keep pitching it to our funding agency. And there was, a chance that they would say no. And then over the last 2 years or so, we folded the funding into something what's called a core program into the Department of Energy. And the core programs are a type of funding resource that are really expected to continue indefinitely. So we still have to repitch it every 3 years, but it's in a much more stable situation than it was as of 5 years ago, where it was like a completely new proposal every single time. So what I would say is that now that Materials Project is a core program and this MP contribs has also been rolled into this core program setup, that we expect that the funding will be more stable. We've also been looking at additional funding sources outside of the U.S. Department of Energy. It's possible that that will happen in the future as well. That will just give us a little bit more resilience in case anything goes on. But again, I would say that the funding situation has actually been getting a little bit more stable over time for materials project. In terms of MP contribs and curation of the data, making sure the data is correct, this is a complicated topic, I would say. It's really hard to know what data is correct, what data is incorrect, who can we trust, who can we not trust. So far, we haven't had too much of a problem because there's been about 27 different public projects. So it's been enough that we could manually, talk to every single person that's been contributing. We have a sense of exactly what the data set is. We kind of know a little bit about whether we can trust it or not. So certainly it's been a process where even though we don't, validate every single data set, certainly we've validated the people that we've talked to, et cetera. As MP contribs gets bigger, it's probably going to become more and more difficult for us to really make sure that every contribution is, well done and validated, et cetera. So I think we'll have to come up with other sorts of ways to, let the user community help decide the trustworthiness of different data sources and be able to flag data that doesn't look correct, et cetera. So far we haven't really had this problem just because MP contribs has been a bit smaller. It's certainly not the major part of the website, et cetera. So it hasn't been the biggest issue so far, but certainly going forward we might have to come up with systems again that allow the users themselves. We're also not experts ourselves in every single topic. So if somebody gives us a bunch of data from a light source, we can't really validate whether it's the experiments were done correctly. So we might have to leverage other people in the community to actually flag data sets, and then we'll have to follow up with them. But it's an interesting topic to think about how to do this, and we certainly don't have all the answers yet.
Thank you.
Okay, so thank you very much, Anubhav. I think we have exhausted the questions from the audience, at least for the moment. In case they have questions, they probably will get in touch with you directly. So thanks again for your time, and
thank you very much.
Yeah,
thank you, Anubhav.
Thank you.
Great, that's great. Yep, nice to be on.
Thank you. So with this, we close the session for today, and then we'll